works at Salvetti University's professor of neurology. Thank you, Marco, for coming.
Thanks, Guido, thanks to the organizers for this kind invitation. I didn't know personally GB Rossi, but listening at the contribution that I heard today, it's clear the legacy, the personal legacy, and also the scientific legacy he left. So I'm really honored to be here today. So I requoted what was written on the program concerning this session, because I think it was really appropriate as far as the story of interferon beta in multiple sclerosis. Some data, very interesting data, that we can build upon and progress from there. So the story began quite similarly as many other stories in therapy of material diseases. It was similar to what happened with repositioning of drugs. You have a drug and you start it and you don't know very well why you're starting this drug for this kind of patients. And in multiple sclerosis, this was the case, because in 1982 now, people thought to try interferon beta, at the time it was interferon alpha, intrathecally in multiple sclerosis. The rationale for trying interferon beta in multiple sclerosis at that time was either concerning a possible viral etiology of the disease, or of course a disease cause of multiple sclerosis. But there was no clear evidence at that time. Curiously, many of you may know that in the experimental model of multiple sclerosis, experimental allergic encephalomyelitis, every drug you try, it works. So it is not considered a very good model for multiple sclerosis. But curiously, when interferon, type 1 interferons were tried in that model, they were among the drugs that performed worse than the others. Nonetheless, since there was perhaps a strong theoretical rationale, experimental efforts continued, and of course this is the first pivotal trial of interferon beta in multiple sclerosis that led to the approval of the drug as the first disease-modifying therapy for this disease. During the years, the focus about multiple sclerosis changed from viruses to autoimmunity in general. And many immunological studies were responsible for this, providing demonstrations of dysregulation of the immune system at various levels. But perhaps more importantly, the role of interference was validated by the first GWAS studies in multiple sclerosis. This is a meta-analysis that was published in Nature Genetics in 2009. And you see, this is the largest GWAS study in multiple sclerosis in 2011. And you see already from the title that, okay, the picture that comes out is for a cell-mediated immune mechanism in this disease. And importantly, again, we find among the 50 genes that at that time were identified by this study, again, the interferon pathways are relevant. This brought, again, to the most recent GWAS to analyze only a set of immune-related loci and identified 48 new susceptibility variants. So Now, at this time, we can think that interferon-beta in multiple sclerosis works through immunological mechanisms. You know, from GWAS you have the snapshot of what happens at the DNA level, but then you also admit some functional correlates. And functional correlates are starting to come, and I'm happy to present here the data from the laboratory of Elena Coccia, who collaborates with us since a long time. And she showed now that a defective toll-like receptor 7 expression can be restored by interferon-beta therapy in multiple sclerosis. Not only this, she also showed recently that interferon-beta impacts actually on the B-cell response to toll-like receptor treatment. And finally, the virus now is coming back somehow, because she was able to show that the Epstein-Barr virus latency gene expression is reduced by, again, interferon-beta therapy. You may know that Epstein-Barr virus is perhaps the most important suspect as being the etiologic agent for multiple sclerosis. So I think these results are extremely relevant for the etiology of the disease. Again, data from this institute, from the laboratory of Francesca Luisi, reinforced the focus on EBV in multiple sclerosis, since Francesca was able to show some years ago that for the first time the presence of Epstein-Barr virus in the lesions within the central nervous system of patients with the disease. So, once more, the importance of viruses in the etiology of the disease, and then other papers came out looking at the effects of interferon on the persistence of the virus. And we don't have clear data so far, but it is interesting now that people are starting to show that interferon-beta is associated with a reduced T-cell response to alpha-1, which is one of the antigens, it's a latency antigen of the virus. Okay, so from this evidence, other groups started trying, okay, if the Epstein-Barr virus is involved in multiple sclerosis, why not to try some antiviral therapies? Unfortunately, among the viruses of the herpes family, Epstein-Barr virus is perhaps less sensitive to this kind of drugs, of course. But anyway, the results were overall negative. But in patients with very active diseases, in subgroups of patients with very active disease, they were able to show some efficacy, at least in this subgroup of patients. Of course, it would be nice to believe that Epstein-Barr virus is the only virus implicated in multiple sclerosis, but this is not the case. We know that viruses have common mechanisms to perturb the immune system, so it is reasonable to think that other viruses may act on the disease in similar ways, though each virus perhaps keeping on some peculiarities. So what we need to understand from the GWAS data and also from data on the biology of virus is really how viruses interact with a predisposing genetic environment in the host. And this can be done today through bioinformatic approaches where you can construct the interactions of virus with the products of the genes in humans. And then you can put together the data of each interaction of each viral agent okay, and see whether within the interactome of each virus there is a statistically significant association with predisposing genes in this disease. And if you do this work, you find that Epstein-Barr virus is associated with the disease here. But you find also, quite unexpectedly, but not so much unexpectedly, because there are epidemiological data that may explain these associations, also hepatitis B virus and HIV. So, looking at this data, you now have a lot of information where you can mine targets, therapeutic targets, that may flank therapies such as interferon and be more specific for etiologic agents in diseases. Of course, there is another level of complication, which is given by the viral genotypes. This is a topic that is not very well investigated so far in multiple sclerosis, but some groups have started working on this, and we have started with the variants in the EDNA2 gene of Epstein-Barr. EDNA2 gene has an hypervariable region of 500 base pairs, and we thought it interesting to start sequencing this region in patients and controls. And what we found was that there were overrepresentations of some subtypes of virus in patients compared with controls. And also an overrepresentation of some newly identified sequences in patients against with respect to controls. Interestingly, this region interacts, and again, the interaction between gene products of the host and the virus once more are important, interacts with, for example, with SMARCB1. SMARCB1 is one of the components of a complex that mediates the cellular antiviral activities and mediates the expression of interferon beta. So if you block this complex, then you can block interferon beta production. And perhaps it is not, it makes sense that a virus that wants to persist in the host tries to address this mechanism and block it. So we have, thanks to the interferon beta studies, we now have a more complete picture about what a drug can do in this disease and what may be the appropriate targets for therapy. Last point, however, again, the genotype study about the virus showed that with longitudinal observations, you see in patients a lot of variability concerning different viral genotypes at different time points. And so this means that perhaps it will be necessary to treat patients for protracted times. Okay, so I will stop here and thank, of course, our collaborators, first of all, Eliana Coccia here and Francesca Rossi too, and Luca Battistini at the Instituto of Santa Lucia, all involved in studies on the Epstein-Barr virus in multiple sclerosis with us. Thank you very much.
Thank you, Marco. Antonina Dolei. Questions?
Hi Marco, thanks for the talk, but you should also remember the role of the human endogenous retroviruses in this disease. We have been working for the last 15 years showing a close parallel between viral load of human endogenous retroviruses of the W family and MS behavior, both in vitro and in vivo, and it has been shown also that the M protein of this retrovirus can reproduce the disease in the ERE model. And by the way, interferon therapy, effective interferon therapy, clears completely the expression of the MW virus. And this has been shown also to be blocked with one single shot of interferon. And of course, is a clear marker of therapy.
You're perfectly right. In fact, of course, this is a strong possible footprint in multiple sclerosis, as well as Epstein-Barr, as well as, I said, many other viral agents. I mean, actually, I believe that it's not a single agent. It's a concurrence of many possible microbes, and yes, you're right. But when I was showing that paper in Nature with the common and specific mechanisms, this is what I meant. I mean, I could have listed endogenous retrovirus by Zoster's and HPV and many others. I mean, it's not a question of what virus is there. I think it's more a question to try to understand globally.
Perfectly right, but this endogenous retrovirus has the neuropathogenic potential. That means a lot of difference. And maybe you know the dual virus hypothesis of EBV waking up the endogenous retrovirus.
Yes, this is right.
Okay. I think if there are no questions, thank you.